Hello. Yeah. Good evening, dear students. Welcome to Get Wallah. So we are running the measuring instruments chapter. So we are discussing the electrical measurements. Today's lecture we are going to start electrical instruments. This is lecture number 3. In the first lecture we have discussed the error analysis. In the second lecture we have started with bridges, and now we are moving to electrical instruments 1. So in the last class, what I am going to discuss here, topics to be covered. Okay, so if you see the topics to be covered, so what are the topics I am going to cover? So we are going slowly into the measuring instruments. In the measuring instruments we are going to discuss the basic working of the PMMC. What are the measuring instruments? We are having the PMMC and moving iron instrument and the dynamometer. These are the major instruments that we are going to cover. Dynamometer. So these are the 3 major instruments in our electrical measurements: PMMC, moving iron and dynamometer. So before going to the topics to be covered, so in the last class I think I have given one question to you. How many of you have done that question? The last class I have given one question to you. How many of you done that question? In bridges, as a last question, I was giving one question to you. How many of you done this question? This was a question in the last session I have given. So those who are present in the previous sessions, they can answer and they can start. Okay. So now if you see this, can you answer this question immediately? Try to answer this question. So what was the thing here given? Deflection sensitivity of the galvanometer is given as 0.2 degree per microampere. The meter resistance is 1000 ohms and the 4 resistors are 400 ohms, and the 4th resistor is changing. Delta R is given as plus or minus 1% of R. So if delta R is taken as 1% of R, so that will be how much? 1 by 100 of R. R is equal to how much? 400 ohms. So that will be 4 ohms. So now if you take this bridge, so what is the bridge configuration now? It is going to be, once the delta R is changed, what is the bridge configuration it is going to be? So this is our 400 ohms. This is our 400 ohms. This is our 400 ohms, and this is our 400 plus something. Okay, na? The supply, yes. So this is 400 plus 4 ohms, 400 ohms, is 400 ohms. Here comes the meter. The meter resistance is 1 kilo ohm. So now the question here is, first of all, what we have to find? He has given the deflection sensitivity of the galvanometer. What do you mean by deflection sensitivity of the galvanometer? I hope all of you are in the Ramzan celebration. A happy Ramzan to one and all. So students are also very less in the live, but those who are watching the session, I am wishing you A happy Ramzan to one and all. So deflection sensitivity of the galvanometer is given. So deflection sensitivity of the galvanometer, what is the meaning of the galvanometer deflection sensitivity? Can anybody tell me what is the meaning of the deflection sensitivity of the meter? Anybody type there? Okay, so can you type what is the deflection sensitivity of the meter? So if you see this, the meter, so here comes the galvanometer current and here comes the deflection in degrees. Deflection in degrees. So the deflection sensitivity of the meter is given as 0.2 degree per microampere. What is the meaning of it? If 1 microampere of current is entering, then the deflection is 0.2 degrees. If 1 microampere of current is entering, the deflection is how much? 0.2 degrees. So now how much current is going to be entered here, that we have to calculate. The first thing is we have to calculate the Thevenin circuit for it. So first of all of you, those who are in the live, so try to do it. So how to answer this? Anybody tell me how to answer this? So first of all we have to calculate the V Thevenins. So to calculate the V Thevenins calculate karo. All of you, V Thevenins. So how to calculate the V Thevenins? So we have to open this bridge circuit. This is 400, this is 400, this is 404. So now if you open the circuit, open the circuit like this. This is 400, 400, 400, 404. This is supply voltage 12 volts. So now V Thevenins is this. So what is a V Thevenin's? V Thevenin's is nothing but quarter bridge. Okay, or else yesterday some Rishabh was asking, can I use the directly voltage division formula? Yes, you can use. So V Thevenin's is 12 into, so these two are in series and these two are in series. So that will be 400 divided by 400 plus this is 800 minus these two are in series. Okay, and 400 divided by 804. So how much it is going to come? Please calculate and tell me. Use the calci and tell me how much we are going to get. The value of it. 400 divided by 800. 400 divided by 804. It is going to become 12. It's coming as 0.29, 0.03 volts approximately. Or directly we can apply the quarter bridge formula also. Why? Because now it is open, means meter resistance is infinite, we can take it. So this can be taken as Vs by 4 into delta R by R, we can take it. So the supply voltage is 12 by 4 and the delta R we can take it as 4 ohms and the resistance we can take it as changeable resistance 400. So 4 of 4 gets cancelled. So 3 by 100, 3 into 10 power minus 2. So 3 by 100, that means 0.03 volts. Same answer aa raha hai na? So when the bridge is open, we can apply the quarter bridge formula. So V Thevenin's is 0.0. The V quarter bridge formula, we got it. So those whoever are watching in the live, can you confirm me whether you got the same answer or not? So V Thevenin's we got it. So let us go for the next for R Thevenin's. So if we go for the R Thevenin's calculation, so what is R Thevenin's? For R Thevenin's we have to short this particular circuit. So we have to short this circuit like this. So if you short this circuit, so this is 400, this is 404, 400, 400, and if you watch these two resistors, so what we can do now, I have shorted this. Okay, I have shorted this. Okay, we shorted, what is going to happen? R Thevenin's we have to calculate. So now this particular 400 parallel, this 400 parallel, this 400 and 404 also parallel. So now if you take 400 into 400 divided by 800, 200 is 400 into 4 divided by 0.4, coming as 400.99. Am I right? R Thevenin's is coming as 401 approximately. Any mistakes, let me know. Any mistakes are there, let me know. So now we got the V Thevenins and R Thevenins. We can calculate the I Thevenins. We can calculate the current. Galvanometer current we can calculate. What is the galvanometer current that we can calculate? Because we need to find out the galvanometer current, for that we have started the V Thevenins and R Thevenins. Now slowly we have to reach to the galvanometer calculation. So what is the galvanometer current? How to calculate? So if you see this as the V Thevenins, and if you see this as the R Thevenins, and if you see this as the galvanometer resistance. So V Thevenins is how much? 12 volts. R Thevenins, V Thevenins is not 12 volts. V Thevenins is 0.03 volts. This is 0.03 volts. And our galvanometer is 1 kilo ohm, that is 1000 ohm. This is the I galvanometer. And the R Thevenins is 401 ohms. So now we can calculate the I galvanometer, that is V Thevenins by R Thevenins plus R galvanometer. So V Thevenins is nothing but 0.03 divided by R Thevenins is 401 plus R galvanometer is 1000. So now what is the current we are going to get? Can you calculate and tell me? So if you check now, 0.03 divided by 401 plus 1000 is going to become as 2.141 into 10 power minus 5. 2.141 into 10 power minus 5. That means you are going to get 21.4 microamperes. Am I right? 21.4 microamperes. Now, from the deflection sensitivity of the meter, see, the galvanometer current is equal to how much? 21.4 microamperes. So what is the deflection? So sensitivity of the galvanometer is given as how much? Sensitivity of the galvanometer. What is the sensitivity of the galvanometer is given in the question? 0.1, 0.2 degree per microampere. So 0.2 degree per microampere. So for 1 microampere current, I am going to get 0.2 degrees. For 21.4 microamperes, how much I am going to get? Into 0.2, 4.28 degrees. So the right answer for this question here is 4.28 degrees. What is this? This is 4.28 degrees. Got it? If anybody's any doubts, you can ask me here. Chalo. Now let us go for the today's topic, that is the measuring instruments. As a part of measuring instruments, majorly in our syllabus we are having the PMMC. So let me talk about this measuring instruments table. Important formulae, let me write here as this as important formulae. For gate reference we need the formulae, important formulae, let me write. So now if you take the name of the instrument and its deflection torque and controlling torque, if we check. So this is the name of the instrument. So let us take the name of the instrument. Instrument, it's a deflection torque, controlling torque, and its application. What are its application? Okay, audio clear hai? Yeah. So what is the mechanism? What is the thing that you have to understand here is there are different measuring instruments are present in the market. So that is the PMMC is one instrument, moving iron is one instrument, and dynamometer is another instrument. But for all the instruments the working phenomenon is same. For all the instruments the working phenomenon is almost the basic concept is same, having deflection torque and controlling torque and application. So if you see the deflection torque, so what is the deflection torque? There are two torques for every measuring instrument. So the first instrument is the PMMC. For PMMC the deflection torque is Vina and the controlling torque is Kc theta. Okay, and the application is it is suitable only for DC. Only for DC. Next, the second comes the moving iron instrument. Deflection torque is 1/2 I square dl/d theta. This is Kc theta. It is suitable for both DC as well as AC. Actually I said to ma'am not to put the class today on Ramjan, but based upon the students' demand she kept up. But here the result is different. But anyway, after the live also you can watch the session. Dynamometer, you can see the dynamometer is quite different. Let me take not dynamometer, let me take electrostatic voltmeter first. You see the electrostatic voltmeter. For electrostatic voltmeter the deflection torque is 1/2 V square dc/d theta. Controlling torque is Kc theta. Is also for DC as well as. Okay, now the same to same if I go for dynamometer, the formula is I square dm/d theta. This is Kc theta. It is for both DC as well as AC. So these are the major outcomes in the GATE exam. So you have to write important formulas first. You have to write the important formulas first. So for PMMC, the deflection torque is bina, controlling torque is kc theta. For moving iron, the formula is half I square dl by theta. Very easy to remember this. Why? Because moving iron works on the concept of self-inductance. So this is the way you have to remember. This works on the concept of change in self-inductance. So here it works on the capacitance. So that is the point you have to understand. That's why we will get here dl by d theta and we will get here dc by d theta. Okay. Dynamometer is M, mutual inductance. So that is the techniques to remember. I square dl by theta is for self-inductance and dc by theta is for capacitance, and electrostatic voltmeter dm by theta is for dynamometer. So if you see the PMMC, basic PMMC, so let us talk about the basic PMMC operations, deflection torque and controlling torque equations. So for PMMC, let us go for the questions directly. So for PMMC, permanent magnet moving coil, the deflection torque is equal to bina and the controlling torque is equal to kc theta. So now at steady state, what is going to happen? At steady state, deflection torque is equal to controlling torque. So that is bina is equal to kc theta. So theta can be taken as bina by kc. So here comes I. So now theta is proportional to I. So the characteristics are directly linear characteristics. So now if I am taking this on x-axis, I am taking the current, and y-axis I am taking the deflection. So the characteristics I am going to get as uniform characteristics. These are the uniform. PMMC is suitable for DC and characteristics are highly linear. Now if we go for the PMMC, major important formulas of range extension of the PMMC. See, PMMC can be suitable as ammeter as well as voltmeter. Range extension for PMMC ammeter, check what are the formulas. See, first let us draw the diagram of PMMC. So these are IM and these are RM. So this is a basic representation of the PMMC. It is having IM and this is the RM. So this is our IM, RM. But the point here is, if you want to extend the range, we need to attach a shunt resistor. You have to attach a shunt resistance. So what is a shunt resistance? You want to attach a shunt resistance. So this is a shunt resistance RSH. So this is I, this is ISH. Okay. So now here we can have a small discussion. By attaching a shunt resistance, the range can be extendable. Okay. The range is going to be extendable. So here if you see this total parallel combination, this is parallel with this. So what I can write here, I can write the VM is equal to VSH. I can write it as VM is equal to VSH. So VM I can write it as IM into RM. VSH is equal to ISH into RSH. Okay, so shunt resistance formula I can write it as IM RM by ISH. So I is nothing but split into two parts, that is IM plus, so I can write this as IM RM, the total divider ISH can be taken as I minus IM. So if I am taking this IM out, I by IM minus 1. So this gets cancelled. So the RSH can be taken as RM by M minus the formula. So shunt resistance formula RM by M minus 1, where M is called multiplying factor I by IM. So which is what we call as multiplying factor for the range extension of ammeter, I by I. Is it clear? Let us go for the range extension of the voltmeter. If you go for the range extension of the voltmeter, range extension of voltmeter. So what is the range extension for voltmeter? If you see, so this is a basic diagram of voltmeter and resistance. The RM, and now if you see this one, this is our RSC, which we call as series resistance. So to extend the range of the ammeter, we have to keep a parallel resistor. To extend the range of the voltmeter, we have to keep a series resistor. That is a major thing you have to understand. So this total I can take it as V. So this voltage will be Vm as total current I, total voltage, the range which can be extendable, I can take it as capital. Okay, so now what I can write here, if you take the V, the expression for V is equal to I into RSC plus RM, and if you take Vm, that will be Im into Rm. So anyway both are same. So if you take the ratio of V by Vm, take the ratio of V by Vm, so that is going to become as I into RSC plus Rm the whole divided by Im into Rm. So these two are going to be cancelled. So this is a multiplying factor. This is RSC by RM plus 1. So M minus 1 is equal to RSC by RM. So the series resistor can be taken as RM into S. So this is the resistor. Got it? So this is a series. So the range extension for the voltmeter, how it can be done? The series resistor I can take, RSC can be taken as RM into M minus. These are the major formulas. Okay. So now based on this, let us go for the questions of the PMMC. So try to answer these questions. Very regularly asked questions these all are. गेट मद्रास 1997 का सवाल है. IIT मद्रास 1997 का क्वेश्चन. An ammeter with input resistance of 50 ohms gives full scale deflection for 50 microamperes current. The input resistance of a 0 to 1 milliampere ammeter obtained by connecting a shunt across the 0 to 50 microamperes will be dash. Option A 50 ohms, option B 25 ohms, option C 50 ohms, option D 2.5 ohms. So how to answer this question? An ammeter with input resistance of 50 ohms gives full scale deflection for 50 microamperes current. So the input resistance is asking the shunt resistance. So let me draw the diagram first. So this is the IM, the RM, the RSH, so this is a capital I. An ammeter with input resistance of 50 ohms. So this is 50 ohms. Gives full scale deflection for 50 microamperes current. So this is 50 microamperes current of a 0 to 1 milliampere ammeter obtained by connecting. So he wants to make this as 1 milliampere range. So see this point, the minimum is the minimum range, this is a maximum. That means you want to convert 50 microamperes current range to 1 milliampere range. So 1 milliampere is greater, so that is the maximum current. So what is asking? Is asking the RSH. So you have to identify that RSH is equal to RM by minus 1. Here I can take it as M as I by IM minus. So here the meter resistance is 50, capital I, 1 milliampere, that is 1 into 10 power minus 3 Im is 50 microamperes, 50 into 10 power minus. So how much I am going to get here? Check it. It's coming around Rm is 50 ohms na, 50 ohms. You want to current 1 milliampere to 50 microamperes to 1 milliampere. Current 2.5 ohms, roughly going to get 2.5. Sorry. Go for one more question. So what is the answer for this question? Try it. ISC Bangalore 2008 का सवाल. A 2 amperes full scale PMMC type DC ammeter has a voltage drop of 100 milliamperes at 2 amperes. Voltage drop of 100 millivolts. Sorry, this is 100 millivolts. Correction. Millivolts. Millivolts at 2 amperes. The meter can be converted to into 10 amperes full scale DC ammeter by connecting a dash. So first of all, let me draw the diagram. So this is the ammeter. So this is the meter resistance Rm, and this is the shunt resistance Rs. Rm, Im. So what is the data given? First you have to extract. A 2 amperes full scale PMMC DC ammeter. So these are 2 amperes. Has a voltage drop of 100 millivolts. So the voltage drop here is the Vm. Okay. So this voltage drop is Vm. Vm is equal to Im into Rm. So Vm is equal to Im into Rm. So that is it is given as 100 millivolts. So from this you can find out the Rm. So these are 2 amperes. So Rm is equal to what? 50 milliohms. So we got the Rm as how much? 50 milliohms. Rm is 50 milliohms. The meter can be converted to 10 amperes. So this should be converted to 10 amperes current. This should be converted to 10 amperes current by connecting a dash. So RSH is equal to Rm by M minus 1. So M can be taken as I by Im minus 1. So Rm I can take it as 50 milliohms, 50 into 10 power minus 3, the whole divided by I is equal to 10 amperes and Im equal to 2 amperes minus. So I think you are going to get how much? 50 into 10 power minus 3 divided by 5 minus 1, 4. 12.5 milliohms in parallel. What I am going to get? 12.5 milliohms in parallel with meter. 12.5 milliohms parallel with. Okay. Option A will be the right answer. So try to answer this question. IIT Kharagpur 1994 question. In the circuit shown in the figure below, the voltmeter is connected across AB. If the voltmeter has a resistance of 1200 ohms, so the voltmeter resistance Rm is given as 1200 ohms. So this Rm is given as 1200 ohms. The measured value differs from the value of dash. So true value is 40 volts. Okay. So if it is 1200 ohms, then what is the diagram? Very network theory question, the basic of networks. So this is a supply voltage. So what is the supply voltage given? 40 volts. These are 40, 200, 300 and 200. So this is the 40 volts and this is 200, 300. This is 200. $300. Next is 200. So now if you take this parallel combination, 300 into this parallel, 300 into 1200 divided by 300 plus 200. This is 300 into 1200 divided by 1500. And this gets cancelled. So what is the answer? So 12 into 300, 3600. 15. So 15 2 ja 30. 240 ohms are. Am I right? 240 ohms. 300 into 1200 by 1500. 3600 divided by 15. Yes, 240 ohms. So now this entire circuit will become like this. So 40 volts and this is 200 and this is 240 ohms. Now if I am taking this part here, so what is the measured value? 240 divided by 442. So how much we are going to get? 240 divided by 440 into 40. 21.81 volts. So question asked here is differs from the true value by what? So the error here is equal to measurement value minus value. Measurement value is 21.1 minus true value 40. Right? Because parallelly 240 आना है ना, so 21.8 minus 40 differs by how much? 18.8. So the answer is differs from, he asked. So 18.18. So these are some good quality questions on the measuring instruments. Okay, let's move for one more question. I will give one question as assignment now. Try to answer this question, IIT Delhi 1998 model. Please take this question as an assignment. Try to give me the answer by tomorrow. Yeah. Try to answer this question. Somewhat you should understand the logic of digital. Okay. So for the two square inputs in the figure, the PMMC meter with read maximum when the phase difference between them is dash. So it is given XOR gate. So XOR gate, what is the truth table of XOR gate? So PMMC has to read means PMMC has to get 1. So how to understand this question? PMMC has to read. How we can get, wait. PMMC has to read, so how to get it? So if you see the XOR gate truth table, the XOR gate truth table, XOR gate truth table, let us take this as X and Y, and this is the output. So XOR will be for the same 0 1. What is the truth table? Let us take here. So if you take the XOR gate truth table, this is, let's take truth table as 0 0 1 1 0. When both are same, the output will be 0. The remaining cases it is 1. That means if it is 0, it should be 1, and if it is 1, it should be 0. Then you are going to get 1, then the PMMC will be reading. So that is not possible when both are in the same phase. So there should be a phase difference. Okay. So how much phase difference? If X is like this, the Y should be 1. This is the X, this is the Y. So it should be like this. This is Y. If this is X, this is 0, this should be 1, this is 1, this should be 0, like that. Okay, that means the phase difference must be T by 2. Take that entirety, phase difference by 2. So that is a very good question, quality question. Okay, that's it. Enough for today. The coming lectures will discuss another topics. Thank you.